Hello there, and welcome to Sleepy Science Stories. Tonight, we are leaving the ground behind. We are moving past the clouds, past the thin blue line of the atmosphere, past the satellites that orbit silently above your head right now. We are moving past the moon, past the cold outer planets, past the edge of the solar system, where the sun's influence fades into the wider dark. And then we are going further still, into the deep and quiet space that stretches in every direction without end. Space is not empty. It only appears that way from here. What looks like darkness from your window is filled with radiation, with particles, with fields of force, with light that has been traveling for longer than the Earth has existed. There are objects out there that make the most powerful things on Earth look insignificant. There are forces that reshape matter itself. There are events so energetic that they briefly outshine entire galaxies, containing hundreds of billions of stars. Tonight, we are asking one of the strangest questions astronomers have ever sat with. What is the most dangerous thing in space? It sounds like a simple question. You might expect a simple answer. A black hole, perhaps, or a supernova, or a collision between worlds. And those things are all genuinely extraordinary. They are all genuinely dangerous. But the deeper you look into this question, the stranger the answer becomes. Because space has a paradox built into it. The most dangerous things out there are also the most creative. The most violent events are also the ones that built everything you see around you. The forces that can end worlds are the same forces that gave rise to worlds in the first place. The explosions that could sterilize planets are the same explosions that seeded those planets with the elements needed for life. That is the strange star paradox. Danger and creation are not opposites in the universe. They are partners. They are the same process seen from two different angles. And once you begin to see that, the cosmos looks different. Not less frightening, exactly, but more coherent, more whole. Tonight we will move slowly through 10 parts of this story. We will look at the sun, which is both your greatest threat and your greatest protector. We will look at black holes, which consume everything and also regulate the galaxies they live inside. We will look at neutron stars and magnetars, at gamma ray bursts and dark matter, at rogue planets and cosmic rays, at the expanding universe and its long quiet ending, and at each step, we will find the same thing, that what seems purely dangerous is never purely dangerous, that the universe does not separate its violence from its generosity. It delivers them together, always. Before we begin, let us think for a moment about what it means to look up at the sky. On a clear night, away from city lights, you can see a few thousand stars with your naked eye. Each one of them is a sun. Most of them are larger and hotter than our own. Some of them are so distant that the light you see left them before humans existed. Some of them no longer exist at all. You are seeing the past when you look at the night sky. Light is not instantaneous. It travels at about 300,000 kilometers per second, which sounds impossibly fast, but is, over cosmic distances, the thing that makes the universe feel ancient and vast. The nearest star to the sun, a small red dwarf called Proxima Centauri, is about 4 light years away. Light from it takes 4 years to reach you. The bright stars in familiar constellations are typically hundreds of light years away. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.5 million light years away. When you look at it, you are seeing light that left it before modern humans existed. Before our species had language or tools or fire in any meaningful form. The observable universe extends about 46 billion light years in every direction. It contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars. The number of stars in the observable universe is estimated to be greater than the number of grains of sand on all of Earth's beaches. And in that vast, ancient, incomprehensibly large space, things are happening. Things have always been happening. things that dwarf everything you have ever experienced or imagined. Explosions that release more energy in seconds than the sun will release in its entire lifetime. Objects so dense that a teaspoon of their material would weigh 1 billion tons. Forces so intense that they distort the very geometry of space and time. And all of this, all of it, following from the same laws of physics that govern the fall of a leaf, and the orbit of a planet, and the beating of your heart. The universe is not a separate, alien thing that exists outside of you. You are inside it. You are made of it. Every atom in your body was created in some stellar process, in the core of a star, in the explosion that followed, in the accumulation of material that became your planet. The hydrogen in the water in your body is almost as old as the universe itself, formed in the first minutes after the Big Bang. You are, in a very literal and measurable sense, ancient and cosmic, and you are here, now, at rest, in a quiet room, on a small planet that has somehow produced the conditions for something like you to exist. That is not nothing. That is, from the perspective of the universe as a whole, one of the rarest and most remarkable arrangements of matter that we know of. So tonight, we will not rush through any of it. We will give each idea the space it deserves. We will move at the pace of a mind that is beginning to let go of the day and settle into something larger and quieter. If you enjoy these gentle journeys through science, you are welcome to like, subscribe, or leave a thought below. It helps other curious minds find their way here, one sleepy soul at a time. But for now, all you need to do is relax. Let your body become still. Let the sounds of where you are soften and recede. Let your breathing slow to a pace that feels easy and natural, and allow your mind to drift upward, gently and without effort, into the dark between the stars. The journey begins now, and there is nowhere else you need to be. Let's begin. Sajim MNT, the sun is trying to kill you, and also keeping you alive. The most dangerous thing in your immediate cosmic neighborhood is also the reason you exist. It is the sun, not a distant black hole 1,000 light years away, not a rogue asteroid somewhere beyond Mars. The sun, your sun, the one that rises every morning and turns the sky orange and gold, is one of the most powerful and genuinely threatening objects you will ever be close to. And at the same time, it is the single thing most responsible for the fact that you are here at all. To understand why the sun is dangerous, you first need to understand what it actually is. Because the sun is not burning in the way that a fire burns. It is not consuming oxygen. It is not producing light the way a candle produces light. What is happening inside the sun is something far more fundamental and far more extreme. At the core of the sun, hydrogen atoms are being compressed under gravity to such an enormous degree that they are forced together and merge. This process is called nuclear fusion. When two hydrogen nuclei fuse, they produce a helium nucleus, and in the process they release a small but real amount of energy. That sounds modest, but the sun is doing this on an almost incomprehensible scale. Every single second, the sun fuses around 600 million metric tons of hydrogen into helium, and in doing so, it converts about 4 million metric tons of matter directly into pure energy, according to Einstein's equation relating mass and energy. That energy radiates outward through layer after layer of plasma, and some of it eventually reaches Earth, about 8 minutes after leaving the surface of the sun, as the warmth on your skin and the light in the sky. But that same fusion process also produces things that are not simply warm and gentle. The sun constantly releases what is called the solar wind. This is a continuous stream of charged particles, mostly protons and electrons, that flows outward from the sun in all directions at speeds of several hundred kilometers per second. This stream is not metaphorical. It is a real, physical outpouring of matter from the sun, and it fills the entire solar system from the sun all the way to the boundary, called the heliopause, where it weakens enough to merge with interstellar space. The sun also emits ultraviolet radiation in quantities that would be immediately damaging to most life on Earth's surface if it arrived unfiltered. Ultraviolet light at certain wavelengths breaks chemical bonds, including the bonds in DNA. Without protection, prolonged exposure would damage genetic material in organisms, disrupt photosynthesis in plants, and destroy the food web that supports most life on land and in the shallow ocean. And then there are solar flares and coronal mass ejections. A solar flare is a sudden, intense burst of radiation from the sun's surface caused by the release of energy stored in twisted magnetic field lines. A coronal mass ejection is even larger. It is an actual eruption of plasma and magnetic field from the sun's outer atmosphere, called the corona, that sends billions of tons of charged material hurtling into space at speeds that can exceed several million kilometers per hour. When a coronal mass ejection is directed toward Earth, it reaches us within 1 to 3 days. When it arrives, it interacts with Earth's magnetic field. Most of the energy is deflected, but some penetrates. Charged particles are funneled toward the poles, where they create the auroras. In moderate events, this is beautiful. In severe events, it can induce electrical currents in the ground and in long conductors on the surface, including power lines and pipelines. A sufficiently strong event can damage or destroy electrical infrastructure across large regions. In September 1859, the largest solar storm in recorded history struck Earth. It is known as the Carrington event, named after the British astronomer Richard Carrington, who observed the solar flare that preceded it. At the time, the most vulnerable technology was the telegraph. The effects were remarkable. Telegraph systems across North America and Europe failed. Some operators received electric shocks through their equipment. Telegraph paper caught fire in some offices. Auroras were visible at latitudes far south of their usual range, including in the tropics, where people who had never seen them before woke in the night thinking it was dawn. If a Carrington-scale event occurred today, with the world's dependence on electrical infrastructure, satellites, GPS systems, and internet connections, the consequences would be far more significant. Some estimates suggest that a severe geomagnetic storm could cause widespread power outages lasting weeks or months in affected regions, with cascading effects on water systems, transportation, food supply chains, and communications. This is not a fringe concern. Space weather monitoring and preparedness is an active area of research and policy. And yet, the sun also created the very shield that protects Earth from most of its own radiation. The heat generated inside the Earth, partly from the decay of radioactive elements left over from the solar system's formation, drives the movement of molten iron in the outer core. That flowing iron generates Earth's magnetic field. And that magnetic field, the magnetosphere, deflects most of the solar wind around the planet, channeling the charged particles safely away from the surface and into the polar regions, where they produce the auroras rather than damage to life. The sun also placed Earth in the habitable zone, the region around a star where liquid water can persist on a planet's surface. Water requires energy to stay liquid. Too little and it freezes. Too much and it boils. The sun provides exactly enough at this distance to keep the oceans in liquid form over billions of years. And liquid water, as far as scientists understand, is one of the most essential conditions for life as we know it. The chemistry of life, the reactions that build and sustain living things, happen in water. Without the oceans, Earth's surface would be a cold and barren rock. So the sun is dangerous. Measurably, verifiably, powerfully dangerous, and it is also your most essential neighbor. Without it, the Earth would be dark and frozen, its oceans locked in ice, its atmosphere thin and cold, with no energy source to drive the circulation of the atmosphere or the cycling of chemicals through the biosphere. With it, the Earth is warm and lit and alive. That tension between the thing that threatens and the thing that sustains is at the heart of everything we will explore tonight. The universe does not offer simple enemies. It offers paradoxes, things that can destroy you and also made you, things that are dangerous by the same mechanism by which they are generous. The sun is just the first example, and it is the closest one. Let your body soften a little more. There is nothing you need to do right now. The sun has set, or is below your horizon, and it is doing its patient work even in the absence of its light. And here you are, warm enough, breathing easily, resting inside the conditions the sun created. Let that feel simple and good. If you ask most people what the most frightening thing in space is, they will say a black hole. And they are not wrong to feel that way. There is something about a black hole that feels deeply unsettling at an almost intuitive level. It is a place where the normal rules break down, a place where even light cannot escape, a place where time itself behaves differently than anywhere else we know of, a place that, once entered, offers no return. But to really understand a black hole, you have to start with what it is made of, or more precisely, what it is not made of in any ordinary sense. A black hole is not a physical object in the way a star or a planet is a physical object. It is, at its core, a region of space where gravity has become so extreme that the geometry of space-time itself curves in on itself. Everything that exists, every particle, every photon of light, is always moving through space-time. And in curved space-time, all paths, even the paths light takes, bend. In a region beyond the event horizon of a black hole, all paths, no matter what direction they seem to point, curve inward. There is no path that leads outward, not because anything is blocking the way, but because the geometry of that region simply does not contain an outward direction. This is what makes a black hole different from just being a very heavy object. It is a place where the structure of space and time has changed. To understand how that is possible, think for a moment about escape velocity. When you throw a ball upward, gravity slows it down and pulls it back to you. If you could throw it fast enough, above a speed called the escape velocity, it would keep moving outward and never return. For Earth, escape velocity is about 11 kilometers per second. For the Sun, it is much higher. As you imagine a more and more massive or compact object, the escape velocity climbs. A black hole is an object whose escape velocity exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing that enters the region inside the event horizon can ever exit. Black holes come in several types, and they form in different ways. The most well understood are stellar, mass black holes. These form at the end of the lives of the most massive stars, those with masses roughly 20 times the Sun or greater. Stars like this burn through their nuclear fuel far faster than smaller stars do. When the fuel is exhausted, the outward pressure that kept the star expanded against gravity disappears. The star's core collapses in a fraction of a second, and the outer layers, suddenly unsupported, fall inward and then rebound outward in a colossal explosion called a supernova. What remains at the center, if the star was massive enough, is a core so compressed that no known force can stop its collapse. It becomes a singularity, a point of effectively infinite density, wrapped in the event horizon. Stellar mass black holes typically range from about 5 to a few tens of times the mass of the Sun. They are scattered throughout galaxies, the remnants of generations of massive stars that have lived and died. Then there are supermassive black holes. These are found at the centers of most large galaxies, including the Milky Way. The one at the center of our galaxy is called Sagittarius A star, and it has a mass roughly 4 million times that of the Sun. In some other galaxies, the central black hole is billions of times the mass of the Sun. How supermassive black holes form is still actively studied. They may have grown through mergers of smaller black holes over billions of years, or through the direct collapse of enormous clouds of gas in the early universe, or through some combination of processes. Their formation remains one of the open questions of astrophysics. There are also intermediate, mass black holes, thought to range from hundreds to hundreds of thousands of solar masses, which may form in dense star clusters. These are harder to detect and confirm, and their existence has been established only relatively recently through careful observations. The danger of a black hole is real, but it is often misunderstood in popular culture. A black hole does not actively vacuum things in. It does not reach out and grab passing matter from a distance. Its gravity follows the same inverse square law as any other massive object. If you were to replace the Sun with a black hole of exactly the same mass, the planets of the solar system would continue in their orbits, essentially unchanged. They would not spiral inward. The black hole would be invisible, and the solar system would be permanently dark and cold. But the orbital mechanics would be the same. The danger comes when you get close, very close. Within a region where the difference in gravitational pull between the near side and the far side of an object becomes extreme. This difference in gravitational force across an extended body is called a tidal force. Near a stellar, mass black hole, tidal forces become lethal at a significant distance from the event horizon. An object approaching would be stretched lengthwise and compressed sideways in a process that has been given the evocative name spaghettification. The object would be pulled apart into a long, thin stream of matter that spirals inward. Near a supermassive black hole, the event horizon is much larger, and interestingly, the tidal forces at the event horizon are actually weaker because the horizon is so far from the singularity. A person falling into a sufficiently supermassive black hole might cross the event horizon without immediately feeling anything unusual. Only later, as they fell deeper, would tidal forces become lethal, but they would never be able to communicate this back to anyone outside. They would be beyond the event horizon. Black holes also radiate. This was proposed theoretically by Stephen Hawking in 1974. Due to quantum mechanical effects near the event horizon, pairs of virtual particles that normally appear and annihilate each other in empty space can be separated by the event horizon, with one particle falling in and the other escaping as real radiation. Over time, this Hawking radiation carries away energy, and the black hole very slowly loses mass. For stellar, mass black holes, the rate is so slow that the universe would need to be many orders of magnitude older than it currently is before a significant amount of mass was lost. For the smallest possible black holes, the evaporation would be fast and explosive. But for the black holes we know of, Hawking radiation is currently undetectable against the background radiation of the universe. What happens to the information about everything that has ever fallen into a black hole is one of the most actively debated questions in theoretical physics. It is called the black hole information paradox, and it sits at the boundary between quantum mechanics and general relativity, two theories that are each extraordinarily successful in their own domains, but that do not yet fully agree with each other when pushed to extremes. Resolving the information paradox may require new physics. It may tell us something fundamental about the nature of space-time, about the relationship between gravity and quantum mechanics, about what information actually means at the deepest level of reality. Some of the best minds in physics have worked on this problem for decades, and while progress has been made, a complete resolution remains elusive. Black holes are dangerous. They are also among the most important objects for understanding how the universe works. They sit at the intersection of the largest and smallest scales of physics. They are where the extremes meet. And they began, many of them, as stars that shone for millions of years before their gravity finally won. Let that settle quietly in you. Everything you see in the night sky that is a star is held up by the same tension a black hole resolves. A star is a postponed black hole, in a sense. Gravity is always waiting. The light we see from stars is the energy released while gravity waits. And when the waiting ends, what remains tells us things about the universe that nothing else could. There is a point between a living star and a black hole, a state of matter that should not be able to exist and yet does. It is denser than anything else in the universe that has a surface. It is smaller than a city, but heavier than the sun. It is called a neutron star, and it is one of the most extreme objects that nature permits. To understand what a neutron star is, you need to follow the life of a massive star to its end. When a star between about 8 and 20 times the mass of the sun exhausts the nuclear fuel in its core, the outward pressure that has supported it against gravity for millions of years disappears. The core collapses. Within a fraction of a second, the inner core goes from roughly the size of Earth to roughly 20 kilometers across. The outer layers, suddenly unsupported, fall inward at a significant fraction of the speed of light and then slam into the now rigid core and rebound outward, producing an enormous explosion, a supernova, that briefly outshines the entire galaxy. What is left at the center is the neutron star. At the extraordinary densities reached during collapse, normal atomic structure cannot survive. Electrons and protons are crushed together and combined to form neutrons. The entire core becomes, in essence, one giant atomic nucleus. But unlike a nucleus, which is held together by the strong nuclear force, a neutron star is held up by a quantum mechanical effect called neutron degeneracy pressure. This is a consequence of the Pauli exclusion principle, a rule in quantum mechanics that states that two identical fermions, a class of particle that includes neutrons, cannot occupy the same quantum state at the same time. When neutrons are packed to extreme density, this principle creates an outward pressure that resists further compression. That pressure is what holds the neutron star up against its own gravity. The properties of a neutron star are difficult to hold in mind because nothing in everyday life provides a useful comparison. A typical neutron star has a mass of about 1.5 times the sun packed into a sphere roughly 20 kilometers in diameter. The density at the center is estimated to be several times the density of an atomic nucleus. A single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. The surface gravity is about 200 billion times stronger than Earth's surface gravity. If you could stand on the surface of a neutron star, which you cannot because you would be flattened into a layer of atoms almost immediately, the gravity would hold you down with a force 200 billion times greater than what holds you to Earth now. The surface of a neutron star is thought to be a crystalline lattice of atomic nuclei surrounded by a sea of free electrons, forming something like an extremely rigid and dense metal. Below the surface, the structure changes. At greater depths, nuclei become more and more exotic, with more and more neutrons relative to protons, until eventually they dissolve entirely into a fluid of pure neutrons. At the very center of the most massive neutron stars, conditions may be extreme enough that even the neutrons break down into their constituent quarks, forming a state of matter called quark matter. This is not yet confirmed by observation, and understanding the interior of neutron stars remains an active area of research. Neutron stars spin, and many of them spin extraordinarily fast. When a star collapses, it conserves its angular momentum, the product of its mass, size, and rotation rate. A star that was rotating slowly over a volume millions of kilometers wide suddenly collapses to 20 kilometers. By the conservation of angular momentum, the rotation must speed up by an enormous factor, the same way a spinning ice skater spins faster when they pull in their arms, but taken to a far more extreme degree. Newly formed neutron stars can rotate hundreds of times per second. When a neutron star has a strong magnetic field, which most do, the magnetic field rotates with the star. This rotating magnetic field generates electric fields that rip charged particles from the surface and accelerate them to extremely high energies. These particles emit radiation in beams that emerge from the magnetic poles of the neutron star. If the magnetic poles are not aligned with the rotation axis, these beams sweep around as the star rotates, like the beam of a lighthouse. When one of those beams sweeps past Earth, we detect it as a precisely timed pulse of radio waves, X-rays, or other radiation. Neutron stars detected this way are called pulsars. Some pulsars are so regular in their timing that they rival atomic clocks in precision. The first pulsar discovered, in 1967, was initially nicknamed LGM-1, which stood for Little Green Men, because its precision was so remarkable that the astronomers who found it briefly considered whether it might be an artificial signal. It was not, it was a neutron star. But the precision of its pulses has since been used for tests of general relativity, searches for gravitational waves, and as a potential navigation system for spacecraft traveling far from Earth. When two neutron stars orbit each other and spiral inward, losing energy to gravitational waves over millions of years, they eventually collide. The collision is called a kilonova, and it is one of the most energetic events in the universe. In 2017, scientists detected both gravitational waves from such a merger and the electromagnetic radiation it produced across multiple wavelengths. This was a landmark moment in astronomy, confirming that gravitational waves and light could be observed from the same event. The 2017 kilonova also confirmed something theorists had long suspected. The extreme conditions in the collision produced the heaviest elements in the periodic table through a process called rapid neutron capture, or the R process. In the collision, free neutrons are captured by atomic nuclei faster than those nuclei can decay, building up heavier and heavier elements in a fraction of a second. The elements produced this way include gold, platinum, uranium, and many others. The kilonova was observed to produce an amount of gold estimated at several times the mass of Earth. This means that the gold in any ring, in any piece of jewelry, in any gold-plated object anywhere on Earth, was created in the collision of two neutron stars somewhere in the history of the universe. It was scattered through space, eventually incorporated into a cloud of gas and dust that became the solar system, concentrated through geological processes on Earth, and eventually mined and shaped by human hands. The chain of events that connects a neutron star collision billions of years ago to a piece of gold you might be holding is one of the most remarkable threads in the entire story of the cosmos. Neutron stars are also the boundary objects of the universe. They are what exists when matter has been pushed as far as it can go without becoming a black hole. They are the limit. And studying them tells us things about the physics of matter at densities we can never recreate on Earth, pushing the known laws of physics to their edges and sometimes revealing that the edges are not where we expected them to be. Let your thoughts settle around that. The heaviest elements in your world, the ones that are rare and beautiful and dense, were made in the most violent events short of a black hole forming. Danger and treasure arriving together in a single flash of light. For a fraction of a second, or perhaps for several minutes, a gamma ray burst outshines an entire galaxy. Not a single star, not a stellar cluster, an entire galaxy containing hundreds of billions of stars, all outshone by a single event occurring somewhere in the universe at distances that can be billions of light years away. When astronomers first detected gamma-ray bursts in the late 1960s, using satellites designed to monitor for nuclear weapons tests, the signals were so powerful and so strange that it took decades to work out what they were and where they came from. Gamma-ray bursts are now understood to be the most luminous electromagnetic events ever observed. They release more energy in seconds or minutes than the sun will emit over its entire 10 billion year lifetime. The photons they produce are in the gamma-ray range, the most energetic part of the electromagnetic spectrum, far beyond X-rays or ultraviolet light or visible light. These are photons with enough energy to ionize atoms and break chemical bonds at distances that would seem impossibly remote. There are two main types of gamma-ray bursts, distinguished primarily by their duration. Short gamma-ray bursts last less than 2 seconds. They are produced by the merger of two compact objects, a neutron star and another neutron star, or a neutron star and a black hole. The same type of event that produces a kilonova, which we discussed when exploring neutron stars, also produces a short gamma-ray burst. The energy is released in jets, narrow beams of radiation that shoot outward from the poles of the newly formed or newly fed black hole at the center of the collision. These jets can be detected across billions of light years when they happen to point toward Earth. Long gamma-ray bursts last more than 2 seconds, sometimes several minutes, and are associated with the collapse of extremely massive stars in an event called a hypernova or a collapsar. In a hypernova, a star with a mass perhaps 40 or more times that of the Sun runs out of nuclear fuel and collapses directly into a black hole rather than producing a neutron star. If the star is rotating rapidly and has the right internal structure, the collapsing material forms an accretion disk around the black hole, and magnetic fields and infalling matter drive jets of energy outward along the rotation axis. These jets punch through the collapsing star and produce the long gamma-ray burst. The energy in these jets is focused rather than emitted uniformly in all directions. This means that the actual total energy involved, when the beaming is accounted for, is somewhat more modest than it initially appears, though still extraordinary. A long gamma-ray burst might release the equivalent of a few solar masses worth of energy during its active phase, a significant fraction of it in the jets. What would a nearby gamma-ray burst mean for Earth? Scientists have modeled what would happen if a gamma-ray burst were aimed directly at Earth from within our galaxy, at a distance of a few thousand light years. At that range, the gamma radiation arriving at Earth could be energetic enough to significantly damage the ozone layer. The ozone layer is the region of the stratosphere that absorbs most of the ultraviolet radiation from the Sun. Without it, ultraviolet light at wavelengths harmful to DNA would reach the surface at much higher intensities. The initial gamma-ray pulse would last seconds to minutes, but the damage to the ozone layer would persist for months to years afterward, as the chemical reactions triggered by the ionization of the upper atmosphere slowly depleted ozone molecules and produced nitrogen oxides that prevent their recovery. During this period, surface life, particularly organisms dependent on photosynthesis or those living in shallow water near the surface, would face significantly elevated ultraviolet exposure. Some researchers have suggested that a nearby gamma-ray burst could have contributed to one of Earth's mass extinction events, particularly the Ordovician, Silurian extinction around 440 million years ago, which wiped out roughly 85% of marine species. The pattern of extinction in that event has some characteristics consistent with an ozone depletion scenario, including the disproportionate loss of organisms in shallow, sunlit water versus deeper water. However, this remains a hypothesis rather than an established fact. The evidence is suggestive but not conclusive. The good news is that known gamma-ray burst sources within our galaxy are rare and are not currently pointing at us. The most commonly discussed candidate, a Wolf-Rayet star system called WR104, located about 8,000 light-years away, appears to be oriented in a way that might direct a gamma-ray burst in our general direction. But the uncertainty in its orientation is large, and 8,000 light-years is a substantial distance. The vast majority of gamma-ray bursts detected occur in other galaxies, at distances so great that even the most energetic possible burst could not harm us. There is something interesting about the way gamma-ray bursts feel from a distance. We detect dozens or more per year. Each one represents an event of almost incomprehensible violence, occurring billions of light years away in a galaxy we will never visit, marking the death of a star that formed and lived and died before the Earth even existed. We detect it as a brief brightening in our gamma ray detectors, a signal, a message from a past so remote it is almost abstract, and yet the physics that produced it is the same physics that governs everything here. The same laws, the same forces. Taken to their extremes, they produce events that make the entire catalog of earthly violence look like a brief flicker. And from here, from the safe and enormous distance of billions of light years, we can simply observe it. We can decode it. We can learn from it what the universe does at its most energetic. There is a kind of privilege in that. The universe is violent on scales we cannot fully imagine, and we are just far enough away from most of it to be able to look. Let your breathing slow. Let the scale of these numbers drift gently past you rather than trying to hold them. You are here, in this quiet space, and the most energetic events in the known universe are happening at distances so vast that their light has been traveling longer than the Earth has been alive. You are safe in the silence of that distance. There is something in the universe that cannot be seen. It cannot be touched. It does not emit light of any wavelength. It does not absorb light. It does not interact with ordinary matter through any of the forces we normally detect things with, except gravity. And yet it makes up roughly 27% of everything that exists in the cosmos. Without it, the universe as we know it would not have formed. Without it, there would be no galaxies, no stars, and no planets. Without it, you would not exist. It is called dark matter. And we have never directly detected a single particle of it. The evidence for dark matter is not based on seeing it. It is based on seeing what it does. And what it does is bend the behavior of everything around it through the one force it does seem to exert, gravity. The story of dark matter's discovery has several chapters, but one of the most important was written in the 1970s by an astronomer named Vera Rubin, working with her colleague Kent Ford at the Carnegie Institution of Washington. Rubin was measuring the rotation speeds of stars at different distances from the centers of galaxies. The expectation, based on the visible mass of the galaxy and the known laws of gravity, was straightforward. Stars near the center, where most of the mass is concentrated, should orbit quickly. Stars near the outer edges, far from the concentrated mass, should orbit more slowly. This is the same pattern seen in the solar system, where Mercury orbits the Sun far faster than Neptune does. But Rubin found something completely different. The stars at the outer edges of galaxies were moving just as fast as the stars near the center, or even faster. They were moving so fast that, based on the visible mass of the galaxy alone, they should have been flung outward into intergalactic space long ago. Something was holding them in, something with mass, a great deal of mass. Mass distributed in a vast halo around the galaxy, extending far beyond the visible disk of stars and gas. Mass that was invisible. This was not the first hint of dark matter. The Swiss astronomer Fritz Zwicky had noticed something similar in galaxy clusters in the 1930s. The galaxies in clusters were moving too fast relative to the visible mass of the cluster to be gravitationally bound together. There had to be more mass than was visible, but Rubin's work on individual galaxy rotation curves was systematic, comprehensive, and difficult to dismiss. Since then, multiple completely independent lines of evidence have all pointed to the same conclusion. Gravitational lensing is one of the most powerful. General relativity predicts that mass curves space-time and therefore bends the path of light. When light from a distant galaxy passes near a massive object, it is deflected. If the massive object is a cluster of galaxies, the light from background galaxies is distorted into arcs, rings, and multiple images. By measuring how much the light is bent, astronomers can calculate how much mass is doing the bending. When this is done for galaxy clusters, the mass required to explain the lensing is consistently 3 to 5 times greater than the mass of all the visible stars and gas combined. The cosmic microwave background provides another line of evidence. This is the faint thermal radiation left over from the early universe, when the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen, and light was able to travel freely for the first time. The cosmic microwave background encodes information about the density fluctuations in the early universe, tiny variations in temperature and density that eventually grew into the large-scale structure of galaxies and galaxy clusters we see today. The detailed pattern of these fluctuations, measured with extraordinary precision by satellites, matches theoretical predictions only when dark matter is included in the models. Computer simulations of the universe's large-scale structure are another test. Starting from the known initial conditions of the early universe, physicists simulate billions of years of gravitational evolution. Models that include dark matter produce a universe that looks like the one we observe, with galaxies arranged in vast filaments and sheets surrounding large empty voids. Models without dark matter produce a universe that does not look like what we see. All of these different methods, using completely different observational techniques and physical principles, point to the same answer: something with mass and approximately the right abundance that does not interact electromagnetically must exist. What it actually is remains unknown. The leading theoretical candidates have changed over the decades as experiments have failed to find the expected signals. Weakly interacting massive particles, called YMPs, were for many years considered the most promising candidates. These would be particles with masses roughly similar to atomic nuclei, interacting through gravity and possibly the weak nuclear force, but not through electromagnetism or the strong force. They would pass through ordinary matter almost entirely without interacting with it, making them very difficult to detect. Enormous detectors have been built underground in mines and tunnels, filled with ultra-pure liquids or crystals, waiting for the rare occasion when a dark matter particle might collide with an atomic nucleus and produce a detectable signal. Decades of searching have not produced a confirmed detection. This has not ruled out YMPs, but it has constrained them significantly and shifted some of the focus elsewhere. Actions are another candidate. These are very light particles, originally proposed to solve a different problem in particle physics called the strong CP problem, which has nothing to do with dark matter, but which turn out to also have the right properties to be dark matter. Sensitive experiments using strong magnetic fields and microwave resonators are searching for the signal that axions would produce if they convert to photons in a magnetic field. Primordial black holes are yet another candidate. These are black holes that might have formed in the early universe from density fluctuations before any stars existed. If they formed in the right mass range, they could constitute some or all of dark matter. Observations of gravitational lensing and gravitational wave detections have constrained how many primordial black holes of various masses could exist. The search continues, and it is genuinely one of the most important searches in modern science, because identifying what dark matter is would fundamentally change our understanding of particle physics and cosmology simultaneously. But even without knowing what dark matter is, we can say with confidence what it did. It shaped the universe. In the early cosmos, dark matter began clumping under its own gravity before ordinary matter could, because dark matter did not interact with the hot plasma of the early universe the way ordinary matter did, and so it was not prevented from clustering by radiation pressure. This gave ordinary matter a head start. When the universe cooled enough for ordinary matter to decouple from radiation and begin falling freely, it fell into the gravitational wells that dark matter had already created. Galaxies formed where dark matter was most concentrated. The cosmic web of filaments and voids traces the skeleton that dark matter built. You exist in a galaxy that formed in a dark matter halo. You exist on a planet that formed in a solar system that formed in that galaxy. The chain of causation runs from the invisible to the visible, from something we have never seen to everything we have ever known. There is something quietly astonishing about that. The thing you cannot see is what made the place where you can see anything at all possible. You have already encountered neutron stars, those city-sized remnants of collapsed stars where matter reaches densities beyond anything in ordinary experience. But within the population of neutron stars, there is a subset so extreme that they deserve their own time tonight. They are called magnetars, and the forces they generate are, by a wide margin, the most intense of any known object in the universe. A magnetar is a neutron star with a magnetic field roughly 1,000 times stronger than that of a typical neutron star. And a typical neutron star already has a magnetic field trillions of times stronger than Earth's. A magnetar's magnetic field is therefore roughly a quadrillion times stronger than Earth's. A quadrillion is 10 to the power of 15. Written out, it is a 1 followed by 15 zeros. To give you a sense of what that means in physical terms, consider what magnetic fields do at different strengths. Earth's magnetic field, at a few hundred microteslas, is enough to align a compass needle and provide a gentle protective influence against solar wind. Hospital MRI machines operate at fields of 1 to 3 Tesla, strong enough to attract ferromagnetic objects with dangerous force. The strongest continuous magnetic fields produced in laboratories on Earth are around 45 Tesla. The magnetic field of a typical pulsar is around 100 million Tesla. The magnetic field of a magnetar reaches 10 to 100 billion Tesla. At these field strengths, things happen that have no analog anywhere else we know of. At distances of hundreds of thousands of kilometers from a magnetar, the magnetic field is strong enough to affect the structure of atoms by distorting their electron clouds. At closer distances, the field exceeds what physicists call the quantum critical field, the field strength at which the energy stored in the magnetic field per unit volume equals the rest mass energy of an electron. Beyond this threshold, the magnetic field begins to affect the vacuum itself, producing effects that have no classical analog and that require quantum electrodynamics to describe. The space around a magnetar is not simply an empty field. It is a region where the fabric of quantum reality is stressed. At the surface of a magnetar, the magnetic field distorts atoms into elongated shapes aligned along the field lines. Because the magnetic force on the electrons exceeds the electrical forces that normally determine atomic shape, the atoms of the magnetar surface are not round. They are stretched. This changes the chemistry and physics of the surface in fundamental ways. How do magnetars form? The details are not completely understood, but the basic picture is that they form from the collapse of particularly massive and rapidly rotating stars. During the collapse, processes in the hot, dense, rapidly convecting interior of the newly formed neutron star can amplify the existing magnetic field by a large factor through a mechanism analogous to the dynamo process that generates Earth's magnetic field in its liquid iron outer core. A rapidly spinning, highly conductive fluid can generate and amplify magnetic fields through the motion of charged particles. In the extreme environment of a newly born neutron star, this process operates at extraordinary efficiency for a brief period, producing the extreme fields that characterize a magnetar. Most newly forming neutron stars do not become magnetars. The conditions required are specific, and many objects that might briefly become magnetars in their first moments may quickly collapse further into black holes if they are too massive. The magnetars we observe are the rare survivors. Magnetars are also unstable in a way that ordinary neutron stars are not. The extreme magnetic field exerts enormous stress on the neutron star crust, the rigid crystalline layer at the surface. Over time, this stress can build until the crust fractures. When it does, the sudden reconfiguration of the magnetic field releases energy in a starquake, analogous in some ways to an earthquake but operating on a neutron star crust that is far more rigid than any rock on Earth and releasing far more energy. Small starquakes produce what are called soft gamma repeater bursts, brief but bright flashes of gamma rays and X-rays. The most extreme events are called giant flares, and they are in a category of their own. The most energetic giant flare ever observed from a magnetar occurred on December 27, 2004. The source was a magnetar called SGR Waitino 6-20, located about 50,000 light-years from Earth on the other side of the galaxy. In approximately 1/10 of a second, this event released more energy than our Sun emits in 250,000 years. The pulse of gamma rays and X-rays that arrived at Earth was intense enough to partially ionize the upper atmosphere, producing a detectable change in ionospheric radio propagation. It was detected by numerous spacecraft throughout the solar system. Despite the distance of 50,000 light-years, it was bright enough that several gamma-ray detectors were temporarily saturated. It briefly outshone every other source of gamma rays in the sky. If a magnetar giant flare of this magnitude had originated from a source within 10 light-years of Earth, scientists calculate that the effects on the biosphere could have been catastrophic. Fortunately, no known magnetar is that close. The nearest known magnetars are at distances of thousands of light-years, far enough that even their most extreme outbursts pose no meaningful threat to Earth. The 2004 event from 50,000 light-years away was dramatic enough to be historically notable as a scientific observation, but it caused no harm to anyone on Earth. Magnetars also provide important tests of physics at extremes. Observations of their X-ray spectra and timing behavior probe the equation of state of dense matter, the relationship between pressure, density, and temperature at neutron star densities. They also probe quantum electrodynamics in strong fields, general relativity in strong gravity regimes, and the physics of dense magnetic fields in ways that cannot be replicated in any laboratory. There is something remarkable about the scale of the forces involved. The same electromagnetic force that lets you pick up a paper clip with a small magnet, when taken to the extreme densities and conditions of a neutron star, becomes something that bends the quantum vacuum and lights up the sky from across the entire galaxy. The underlying force is the same. The universe simply offers a far wider range of conditions than anything we experience on Earth, and in those extreme conditions, matter and energy do things that feel almost impossible. But they are not impossible. They follow from the same equations. They are the same physics, just further along the scale than we normally think to look. Not every planet orbits a star. There are planets drifting through interstellar space right now, worlds without suns, traveling alone through the dark between the stars. They carry no light of their own. They reflect nothing. They are invisible against the black of space, unless you know exactly how to look for them. And there may be more of them in the Milky Way than there are stars. These are called rogue planets, or free, floating planets, and they are one of the quieter and more thought-provoking discoveries of the last few decades. How does a planet become a rogue? The most common mechanism appears to be gravitational ejection during the formation of a planetary system. When a solar system is young, the dynamics are chaotic. Multiple large bodies are growing from the same disk of gas and dust. They interact gravitationally. They collide, merge, scatter, and in some cases send each other onto hyperbolic trajectories that carry them out of the system entirely. Computer simulations of solar system formation consistently show that gravitational ejections are common. Many forming systems eject one or more large bodies during the first 100 million years of their existence. Our own solar system may have participated in this process. Some models of the early solar system suggest that 5 large planets formed in the outer solar system, not 4. In this scenario, gravitational interactions between these 5 bodies during a period of orbital instability led to one being ejected into interstellar space. The current stable configuration of Jupiter, Saturn, Uranus, and Neptune may have required the loss of a 5th member to achieve. If this is correct, there is a rogue planet somewhere in interstellar space that was once a member of our solar system, now traveling alone through the galaxy with no star to orbit and no record of its origin. Rogue planets can also form directly from the collapse of small gas clouds that are too compact to form a star. These objects exist on the boundary between planet and brown dwarf, a class of object that is more massive than a planet, but not massive enough to sustain hydrogen fusion. The distinction between a very large planet formed through this process and a small brown dwarf is partly a matter of definition, and the boundary between the two categories is blurry. Detecting rogue planets is genuinely difficult. They emit almost no radiation. They are cold and dark. They cannot be seen against the black background of space through ordinary imaging. The primary technique used to find them is gravitational microlensing. When any massive object passes in front of a more distant star as seen from Earth, the gravity of the intervening object bends and temporarily focuses the light from the distant star, producing a brief brightening. The shape and duration of this brightening depends on the mass of the lensing object. When the brightening occurs without any visible star at the lensing position, this is evidence of a dark, massive object consistent with a rogue planet. Microlensing surveys have found numerous candidate rogue planets over the years. Statistical analyses of the frequency of these events suggest that rogue planets may be quite common in the galaxy, possibly more numerous than stars. The uncertainties are large, but even conservative estimates suggest billions of rogue planets in the Milky Way alone. In 2023, observations with the James Webb Space Telescope of the Orion Nebula revealed dozens of free, floating planetary mass objects in that star-forming region. Some appeared to be paired with other similar objects, orbiting each other without any parent star. These paired rogue planets, called Jupiter Mass Binary Objects or JUMBOs by the team that found them, were unexpected and raised new questions about formation mechanisms that are still being worked through. What is the danger of rogue planets? On timescales of billions of years, the possibility of a rogue planet passing through our solar system or close enough to gravitationally perturb it is real but small. The outer solar system contains the Oort cloud, a vast spherical shell of comets extending perhaps 100,000 astronomical units from the Sun. A rogue planet passing through or close to the Oort cloud could gravitationally perturb comets, sending some of them on trajectories that bring them inward toward the inner solar system. If enough comets were sent inward, some could reach Earth's vicinity. However, the probability of a rogue planet passing close enough to matter on any human, relevant timescale is extremely small. The average distance between stars in our part of the galaxy is several light years. The density of rogue planets, while possibly large in an absolute sense, is still tiny compared to the vast volume of space. Close encounters are rare on stellar timescales and even rarer on human ones. What rogue planets are more interesting for, beyond the question of danger, is what they tell us about the range of conditions under which planets can exist and potentially persist. A large rogue planet, formed with a sufficient abundance of radioactive elements in its rocky core, would generate internal heat through radioactive decay. This internal heat could persist for billions of years. If the planet is large enough to retain an atmosphere, that heat could prevent the atmosphere from collapsing entirely to the surface. And if the internal heat and pressure are sufficient, liquid water could potentially exist beneath a deep ice shell, kept liquid not by sunlight, but by internal warmth. This is not as far-fetched as it sounds. Jupiter's moon Europa maintains a liquid ocean beneath its ice shell due to the tidal heating caused by Jupiter's gravity. A sufficiently large rogue planet, with a radioactively heated interior, could maintain liquid water in a similar way, completely independent of any star. Such a planet would be a world with no sky that any surface-dwelling organism could see through, no sun rising, no seasons driven by orbital mechanics. Just the cold, dark exterior of ice and rock, and somewhere beneath, perhaps, warmth and water and whatever chemistry that combination permits. This is speculative. We do not know whether life can arise or persist in such conditions. But the possibility is grounded in physics and chemistry that we understand, and it represents one of the more imaginative corners of astrobiology. A world that has been traveling alone through the dark between stars for billions of years, carrying its ocean beneath a shell of ice, is one of the stranger and more quietly moving images that astronomy allows. There are possibly billions of such worlds in the galaxy, each of them a record of a solar system that once was, each of them moving patiently through the dark toward nowhere in particular, for as long as the universe permits. Let your thoughts soften around that image, a cold, dark world traveling quietly through the space between stars. And here you are, on a world with a sun, with warmth, with the light of a sky that changes every day. That is not a small thing. That is, by cosmic standards, a remarkable circumstance. Right now, as you lie still, particles are passing through you. Not metaphorically, literally. High-energy particles from space, called cosmic rays, are continuously passing through your body. Most of them are protons or the nuclei of atoms, moving at speeds approaching the speed of light. They arrive from all directions. They pass through the atmosphere, through your roof, through you, and into the ground below, and most of them continue onward without depositing any energy you could detect or feel. You cannot sense them. They leave no sensation. They cause no immediate harm at the natural background levels that reach Earth's surface. But they are real, they are everywhere, and they carry information about some of the most violent events in the universe. Cosmic rays were discovered in 1912 by an Austrian physicist named Victor Hess. At the time, it was known that there was a background of ionizing radiation at Earth's surface, radiation capable of knocking electrons off atoms and making them electrically charged. The assumption was that this radiation came from radioactive minerals in the ground. If that were true, the radiation should decrease as you rose higher above the ground and moved farther from the source. Hess tested this directly by flying in a balloon to an altitude of about 5 kilometers and measuring the ionization rate at various heights. He found the opposite of what the ground source hypothesis predicted. Above a few hundred meters, the radiation increased with altitude. The higher he went, the stronger it became. The source was not below, it was above, it was coming from space. We now know that cosmic rays are mostly protons and heavier atomic nuclei that have been accelerated to extremely high energies by processes in space and are constantly streaming through the galaxy and through our solar system. A small fraction are electrons, and an even smaller fraction are gamma-ray photons, though those are typically classified separately. The energies of cosmic rays span an enormous range. At the low end, solar cosmic rays are produced by energetic events on the Sun, with energies in the range of millions to hundreds of millions of electron volts. These are the particles most relevant to radiation exposure for astronauts and for electronics in orbit. At higher energies, galactic cosmic rays come from within the Milky Way and extend up to energies of roughly 1,000,000 trillion electron volts per particle. And at the very top of the spectrum, ultra-high-energy cosmic rays arrive with energies exceeding 10 to the power of 20 electron volts per particle, which is roughly equivalent to the kinetic energy of a well-hit tennis ball concentrated into a single subatomic particle. That last comparison is worth sitting with for a moment. A single proton, a particle with a diameter roughly 100,000 times smaller than a hydrogen atom, carrying the kinetic energy of a tennis ball. The mechanism that could accelerate a particle to that energy is not fully established, and identifying the sources of the most energetic cosmic rays is one of the open problems in high-energy astrophysics. Supernova remnants are well-established sources of lower to intermediate energy cosmic rays. When a star explodes in a supernova, the expanding shockwave travels outward through the surrounding gas at speeds of thousands of kilometers per second. Charged particles can be trapped near this shockwave, repeatedly crossing it and gaining energy each time in a process called diffusive shock acceleration. Over thousands of years, as the remnant expands, particles can be accelerated to energies in the range of cosmic rays. The total energy budget of supernovae in the galaxy is consistent with explaining the observed flux of cosmic rays up to certain energies. At higher energies, other mechanisms and sources are invoked. Active galactic nuclei, the regions around supermassive black holes that are actively accreting matter and producing powerful jets of plasma, are thought to be capable of accelerating particles to much higher energies. Gamma-ray bursts, which we have already discussed, are another candidate for the most extreme end of the cosmic ray spectrum, and pulsars and magnetars contribute through their intense magnetic fields and winds of accelerated particles. When a cosmic ray enters the upper atmosphere, something visually interesting happens even though you cannot see it. The cosmic ray particle, moving at nearly the speed of light, collides with an atom in the upper atmosphere and produces a shower of secondary particles. These secondary particles, pions, muons, electrons, photons, and others, each carry a fraction of the original energy and continue moving downward. Each of them can produce further collisions and further secondary particles. Within milliseconds, what began as a single particle becomes a cascade of billions of particles spreading outward in a cone as they move downward through the atmosphere. This cascade is called an extensive air shower. The secondary particles spread outward in a disk that can be kilometers across by the time it reaches the ground. Large arrays of detectors spread across hundreds of square kilometers, like the Pierre Auger Observatory in Argentina, are designed to detect the arriving particles from these showers at many points simultaneously. By measuring the distribution of particle arrivals in time and space, physicists can reconstruct the energy and direction of the original cosmic ray that started the cascade. The danger of cosmic rays is context-dependent and mostly modest for people living on Earth's surface, where the atmosphere and the magnetic field together provide substantial shielding. At sea level, the dose of ionizing radiation from cosmic rays is a small fraction of the total natural background radiation that everyone receives, which also includes radiation from radon gas, from naturally occurring radioactive elements in soil and building materials, and from medical imaging procedures. But the situation changes for people outside Earth's protective envelope. Astronauts on the International Space Station, in low Earth orbit, receive roughly 10 times the radiation dose per day that people on the surface receive, partly from cosmic rays that the orbit does not fully shield. On a mission to Mars, with no planetary magnetic field and only a thin atmosphere at the destination, the accumulated cosmic ray dose over a 2 to 3-year mission would be significant. Current shielding technologies using spacecraft structure can reduce it but not eliminate it. This is one of the genuine engineering and health challenges of long-duration human spaceflight. There is also a more subtle role for cosmic rays in the story of life on Earth. Cosmic rays are a source of genetic mutations in living organisms. Most mutations cause no immediate harm and are repaired by cellular machinery. Some contribute to cancer, and occasionally, over geological time, a mutation proves beneficial and is selected for by evolution. The background mutation rate from cosmic rays has been part of the environment of life on Earth for billions of years. It is possible, though difficult to quantify, that cosmic ray-driven mutations have contributed to the genetic diversity that has allowed evolution to explore the range of body plans and biochemistries that we see in the history of life. Cosmic rays carry information from the most energetic places in the universe to instruments we have built on the ground and in space. Each particle is a messenger, however difficult to read. The direction it came from, its energy, its composition, all carry clues about where it was made and what accelerated it. Reading those clues requires large experiments, careful statistics, and patience over years and decades. But the picture that emerges is a universe full of accelerators operating at energies we cannot approach with any technology we have built, producing particles that cross the galaxy and pass through your body without stopping. You cannot feel them, but they are there, and they have been passing through living things on this planet for as long as living things have existed. Of all the things we will consider tonight that might be called dangerous, the most patient is the universe itself. The universe is expanding. Everything that exists is embedded in the fabric of space-time, and that fabric is stretching. On the scale of individual galaxies, gravitational forces keep structures bound together. The Milky Way and the Andromeda Galaxy are actually approaching each other because gravity is stronger than the expansion on their scale. But on the scale of galaxy clusters and beyond, the expansion of space dominates. Distant galaxies are moving away from us, and the farther away they are, the faster they recede. This was first established observationally by Edwin Hubble in 1929, using measurements of the velocities and distances of galaxies beyond the Milky Way. The relationship he found, which is now called the Hubble-Lemaitre law, showed that velocity is proportional to distance. A galaxy twice as far away is receding twice as fast. This is not because galaxies are moving through space in a classical sense. It is because the space between them is expanding. Every unit of intergalactic space is growing. The galaxies themselves are not moving through their local surroundings. It is the medium they are embedded in that is stretching. For most of the 20th century, the assumption was that this expansion must be slowing down. The mutual gravitational attraction of all the matter in the universe should act like a brake, pulling everything back toward each other and decelerating the expansion. The question was not whether the expansion was slowing, but whether it was slowing fast enough to eventually reverse and cause a recollapse, the big crunch, or slow but not reverse, leading to an ever more dilute universe. In 1998, two independent research teams studying distant supernovae as distance markers made a discovery that appended this picture entirely. These supernovae, called Type Ia supernovae, are useful as distance indicators because they have a consistent intrinsic brightness, which means their apparent brightness tells you how far away they are. When the teams measured the distances and recession velocities of these distant supernovae, they found that the supernovae were fainter than expected. They were farther away than they should have been for a universe decelerating as expected. The expansion was not slowing down. It was speeding up. The universe is not just expanding, it is accelerating. Whatever is driving this acceleration was given the name dark energy, and it accounts for roughly 68% of the total energy content of the universe. It is the dominant component of the cosmos, and it is the one we understand least. Dark energy appears to behave like a property of space itself, a kind of energy density inherent to the vacuum that does not dilute as space expands, unlike matter or radiation. Its value is consistent with what is called the cosmological constant, a term Einstein introduced into his equations of general relativity in 1917, initially to produce a static universe, and then famously abandoned when Hubble's observations showed the universe was not static. Now, nearly a century later, Something like the cosmological constant appears to be real after all. The physical origin of dark energy is not understood. Quantum field theory predicts that the vacuum should have an energy density due to quantum fluctuations, but the predicted value is many orders of magnitude larger than what is observed. Reconciling this is one of the deepest unsolved problems in theoretical physics. Various alternative explanations, including modified theories of gravity, dynamical scalar fields called quintessence, and others, have been proposed, but none has been confirmed. What dark energy means for the long-term future of the universe is profound. On timescales of billions of years, the accelerating expansion will carry distant galaxies beyond our observable horizon. The speed at which space is expanding will eventually exceed the speed of light at great enough distances, and light from those galaxies will never reach us. The universe will appear to grow emptier, not because galaxies vanish, but because they move beyond what can ever be seen from here. Over trillions of years, even the galaxies of our local group, which are gravitationally bound to us, will merge with the Milky Way into a single large elliptical galaxy. That merged galaxy will be alone in a universe that, from its perspective, is otherwise dark and unreachable. Stars will exhaust their fuel. The era of star formation will end as the gas reservoirs that form new stars are depleted. The last generation of red dwarf stars, the smallest and most slowly burning, will glow for trillions of years before cooling to dark remnants. White dwarfs, the remnants of stars like the Sun, will slowly cool over tens of trillions of years into cold, dark objects called black dwarfs. Neutron stars will cool, and black holes, over timescales measured in googles of years, far longer than anything else we have discussed tonight, will slowly lose mass through Hawking radiation and eventually evaporate entirely. What remains, at the very end of this process, is a universe at maximum entropy. All matter has either been incorporated into black holes or radiated away as diffuse low-energy photons. The black holes have evaporated. The universe is uniformly cold, uniformly dilute, and there are no further energy gradients to drive any processes. No stars, no planets, no chemistry, no structure. Just an expanding void of photons, and perhaps a scattering of fundamental particles, growing ever more dilute in an ever larger space. This is sometimes called the heat death of the universe. The name is a bit misleading because the final state is cold, not hot. It refers to thermodynamic equilibrium, a state of maximum entropy from which no further useful work can be extracted. It is the quietest possible ending, not a bang, not a collapse, simply a gradual fading over timescales so long that the current age of the universe, nearly 14 billion years, would represent an almost infinitely small fraction of the total duration. And yet, none of this is relevant on any timescale that touches human life, human civilization, or even the lifespan of the Sun. The Sun has about 5 billion years of hydrogen fuel remaining. Life on Earth, assuming nothing else disrupts it, has hundreds of millions of years of hospitable conditions ahead. The heat death of the universe is separated from the present by an interval of time so vast that it makes the current age of the universe look like a passing moment. The long arc of the universe is not a threat to you. It is simply the largest possible frame within which to understand where you are. And in that largest possible frame, you are here, now, in the early period, when the universe is still young and active and full of stars. The universe is telling its best stories right now. The era of complexity, of stars and planets and chemistry and life, is happening in this part of the timeline, not at its end. You are early. You are in the bright part of the story. And the long quiet end is so far away that it has no bearing on this moment, or any moment you will ever know. We have traveled far tonight. From the surface of the Sun to the interior of a black hole. From the spin of a neutron star to the invisible web of dark matter. From the crack of a magnetar crust to the lonely wandering of a rogue planet. From the invisible particles passing through your body right now to the long, quiet end of the universe itself. We have covered enormous distances and even more enormous timescales. We have looked at forces so extreme that they have no analog in everyday experience. And we have asked, at each step, whether these things are dangerous. The answer has always been yes. And the answer has always been something more complicated than yes. Because at every step, we have found the same pattern. The things that threaten are the same things that created. The forces that can end are the same forces that began. The violence is inseparable from the generosity. And that is the strange star paradox that has been running beneath everything we have discussed tonight. Let us follow it through, one more time, slowly. The sun, which is the most immediately threatening cosmic object in your neighborhood, capable of producing flares and ejections that could damage your infrastructure and bathe your surface in harmful radiation, is also the reason your planet has liquid water. It is the energy source that drives the entire biosphere. It is the light that enters leaves and becomes sugar and enters animals and becomes motion and enters you and becomes thought. Without the sun's danger, without its fusion, without its radiation, there would be nothing here to be threatened. The threat and the gift are one. Supernovae, which are the most violent events that occur regularly within galaxies, which can briefly outshine their entire host galaxy and bathe surrounding space in lethal radiation, are also the furnaces that created most of the elements heavier than oxygen in the periodic table. Carbon, oxygen, nitrogen, silicon, iron, calcium, all of the elements that make up living things and rocky planets and the air you breathe, were forged in stellar cores and then scattered across space by supernovae. You are made of supernova debris. Your bones are calcium made in a star. Your blood is iron made in a star. The oxygen you are breathing right now was made in a star and scattered by a supernova before being incorporated into the gas cloud that became the solar system, that became this planet, that became you. The same explosion that could sterilize worlds was necessary for those worlds to contain the chemistry of life. Black holes, which are the objects we most commonly associate with total and irreversible destruction, also regulate the growth of galaxies. Supermassive black holes at the centers of galaxies, as they consume surrounding matter, release energy in jets and radiation that heats the surrounding gas. This heating prevents the gas from cooling and collapsing into new stars too quickly. Without this feedback mechanism, the early universe would have produced stars far more rapidly, and the galaxies that resulted might have been very different in structure. The stable, long-lived galaxies with slowly burning stars like the sun, which provide the consistent energy output needed for life to evolve over billions of years, may owe their existence partly to the regulating influence of black holes. The most destructive objects in the universe helped create the conditions for stable, slow, burning stars to exist. Neutron star mergers, which are among the most violent collisions in the universe, producing gamma-ray bursts, gravitational waves, and kilonova, are the factories where gold and platinum and uranium were made. Every piece of gold jewelry, every platinum catalyst, every uranium fuel rod was created in the collision of two neutron stars. The violence made the treasure. The death made the material of human civilization. Gamma-ray bursts, which could sterilize life on planets within their range, also ionized the early universe in ways that may have been important for the formation of the first structures. They may have influenced which regions of the early universe were available for galaxy formation. The same events that end worlds in other galaxies may have contributed, from sufficient distance, to the conditions that allowed our galaxy to form as it did. Dark matter, invisible and unknown, built the skeleton on which all visible structure formed. It seeded the universe with the density variations that gravity could amplify into galaxies and galaxy clusters. Without dark matter, the universe would be more uniform, more diffuse, less structured. There would be fewer concentrations of matter, fewer stars, fewer planets. Dark matter did not threaten anything. It built everything. And the expanding universe, which will eventually carry all other galaxies beyond our reach and end in the quiet dissolution of all structure, also created the conditions for everything we know. The rapid expansion in the early universe cooled the hot plasma of the Big Bang at precisely the right rate for protons and neutrons to form, for hydrogen and helium to be synthesized, for the seeds of galaxies to be planted. Expand too fast and nothing can clump together. Expand too slowly and everything collapses back before structures can form. The rate of expansion was, in a meaningful sense, exactly what was required for complexity to arise. The same process that will end everything began everything. This is the paradox. And it is not a coincidence. It is a feature of how the universe works. The universe is governed by laws that are indifferent to outcomes. Gravity pulls. Nuclear forces bind and repel. Electromagnetism connects charges. Thermodynamics pushes entropy toward its maximum. These laws do not choose between construction and destruction. They do not distinguish between building up and tearing down. They simply operate. And the same operation that tears a star apart can scatter the materials for new stars. The same force that crushes matter into a neutron star also holds together the atoms in your body. The same expansion that will end the universe created the space in which everything beautiful and complex has happened. You are here because the universe is violent. Not in spite of it. Because of it. The iron in your blood was made in the core of a star that lived for millions of years and then exploded. The calcium in your bones was made in a star. The oxygen you are breathing was made in a star. The carbon in every molecule of your DNA was made in a star. These elements were forged by the same processes that could, in a different context, sterilize worlds. They traveled across space for billions of years, through clouds and gravity and solar winds, before being incorporated into the solar system, before being concentrated on Earth, before being assembled by chemistry and biology over hundreds of millions of years into a form that could breathe and think, and listen to the story of where it came from. You are ancient stellar fire that has been rearranged by time and chemistry into something that can feel the warmth of a sun and wonder about the stars. That is not a small thing. That is, in a very real sense, the most extraordinary outcome the universe has produced that we know of. Not because you are the center of anything, but because here, in this small corner of a vast and mostly empty and mostly violent cosmos, something happened that could look back at the whole and understand some of it, and be moved by it. The most dangerous things in space made you possible. And now you are here, in the quiet, with the science settling gently around you like light from stars that no longer exist. Now you do not have to hold any of this tightly. Let it drift into a softer shape. Imagine the universe continuing on without your attention. Stars burning in the dark. Neutron stars spinning. Dark matter drifting through galaxies it can never touch. Rogue planets moving through the cold between the stars. And here, on this small warm world with its single large moon and its just right distance from its steady yellow star, you are still. Your body is heavy and calm. Your breathing is slow. The cosmos does not need your vigilance tonight. It has been doing this for nearly 14 billion years without any help. The forces that built you are still running. The stars that made you are still burning, many of them. The universe is still in its bright chapter, still making complexity, still offering the conditions for things like you to exist and rest and look up. If you enjoyed this sleepy science journey, you might like, subscribe, or leave a thought in the comments, so other curious minds can find their way here. And if you are still awake, there will be another journey waiting when you are ready. But for now, let the last of the day go. Let your thoughts become slow and quiet. Let the science become something you feel rather than something you hold. Rest well. Sleep well. Good night.